Okay, welcome everyone. This is the final lecture before the reading week, and I will have one assignment for you. This is slightly longer, but it's a good time to try to sort out all these concepts. And we have exercise class this week, and we will also have exercise classes on the 8th of April and the 9th of April. Then we come back to finish the final 2 weeks of the term. Okay, so we are really approaching the end of this course, and the progress is good. And let's see how far we can move forward. Okay, so this is what we discussed on Monday. So we solved. Remember, we solved the particle in the box problem, and we went through all this familiar business. So writing down the solution, discussing the solution, the allowed energy levels, and we come up with this density of states. Okay, so this is these n's are the quantum number n that you use to label your energy levels. And here, this is a 2D case, and to fully specify a state, you need to give nx and ny independently. That's why you have all these dots here, and each dot is an allowed energy state. Okay, so we talk about that, and then later in the end of the lecture, someone told me you have seen this before in quantum mechanics. So that, which is good. This is a very important concept for this course. I introduce it this way because maybe this is more intuitive. But you will see this again and again. In particular, if you do solid state physics, you cannot escape from density of states. This is something solid state physicists talk about all the time. So for future reference, I would like to just make a few remarks. So remember how we get these results, yeah? We got this result by solving this kind of problem, right? Particle in a box. I really mean a box, right? So we put 0 to A, and if you solve the Schrodinger equation, a time-independent Schrodinger equation, honestly, you get the wave functions and you get the energies I showed you the other day. But you know, if you want to discuss the wave function, you need to also consider the boundary condition. And something I didn't stress, but it's implicit, is that we are using the so-called box boundary condition. This is really what I meant, a particle in a box. The particle really is inside a box. So box boundary condition. And then the solution will be standing wave. Standing wave. Okay, but this is not a very convenient boundary condition for solid state physics. We don't like to use this kind of boundary condition. What we prefer is to eliminate the boundary. How do we do that? Okay, box boundary condition. What do you mean by that? What do we want? What we want is the wave function at 0 has to vanish. Okay, so the wave function has to vanish at 0 and has to vanish at A, which both of them are the boundary of the box. The particle cannot escape infinite potential here. Okay, so this is one way to do that, and indeed this is I went through this process. The other one is to look at a periodic boundary condition. Periodic boundary condition basically means if I have a particle reaching A, magically it will come back from 0. Okay, and usually we also, for solid state physics, we also like to put 0 in the middle to make it more symmetric. But this doesn't matter too much. Just remember, therefore, if you change the position of the box, your wave function can take different form. For example, it can change from sine to cosine when you have the standing wave solution. Okay, but it doesn't matter. If you have this, then what we will get is the traveling wave. Traveling wave solution. Okay, what do I mean by periodic boundary condition? So basically, it's very similar, but be very careful. What I want is to demand the wave function to be continuous at this boundary. And I imagine that after I reach A, I come back from 0. So I just have to imagine I make this many copies of this. I would just make another copy and align 0 to A here, and then another one, another one, another one. So when I reach A, I basically go back to 0. That's it. I do not demand any value. So whatever the value it is, it has to be continuous. That is the periodic boundary condition. If you solve it, you will get exponential. And that is the traveling wave solution. And in tomorrow's exercise class, I have asked the TA to solve this problem using the periodic boundary condition. And I want you to pay attention on what would be different from my treatment and what will be the same. If you have done this properly, surely this is just the you just choose to describe the system differently. So your thermodynamic should not change, your statistical mechanics should not change. You count it differently, fine, but then in the end, some result should be the same. Okay, so your job tomorrow is to pay attention on the similarity and the differences. Okay, and please pay attention on that, because when I talk about metal, I would like to use this boundary condition right away and to give you something called the Fermi surface. And that requires me to develop this language, but I do not want to start from scratch. Okay, so tomorrow's exercise class provides this link. Okay, so coming back to the box boundary condition, which we'll be using for this chapter, you probably remember this is the number of states below a fixed energy E or epsilon. Okay, and in the class, I think I use N, big N. But in the note, I use G, but and this G is related to this G, because how do you obtain this density of states in energy? You take the derivative. That's why the symbol G appear here. This N is a number, but not to be confused by the total number of the particle in the system. That is why you need to read this carefully. Okay, so now the interpretation, this interpretation is important. You have G of energy times D of energy. What is the meaning of this product? This product tells you the number. It's a dimensional quantity, dimensionless quantity when you take the product like this. This is the number of states, and it's the number of states between energy epsilon and epsilon plus D epsilon. Okay, so this is important interpretation. And in my note last time, you can look at it again. I call this dn, the differential of n, right? This is a number. Is a number in the in the differential increment of energy. Okay, so and the last point to note is we got this result by putting in some numbers. What we have is the number of states. The number of states is much greater than the number of energy states available for you. Is much greater than the number of particles. Okay, this justify the treatment of the dilute gas. Okay, what do we want to do today? What we want to do is to get the distribution function for this gas particle. So the n is to get the distribution function. Distribution function. So since we have a lot of energy levels, energy states, and most of them are empty, right? Because of this treatment here. I remember for my very conservative calculation last time, I say if you have 7 million states, only 35 will be occupied. And this is the number I gave you, 7 million, which is a population of Hong Kong, roughly. And we only have 35 cars. Or maybe more easy to resonate with you is in this 7 million population, we only have 35 masks. That would be a number that you will be able to appreciate. Okay, so these energy states are mainly empty. So we are going to do some trick here. So we are going to look at one particular bundle. This is called a bundle. Okay, so this is the kth bundle. Okay, I have a lot of energy level. So I'm going to cut it in a way that I'm going to group them because they are empty anyway. I'm going to group them. And this is my bundle. Okay, this is one of the bundle. I can choose not to group them, but there's a reason why we want to do it this way. The reason we want to do it this way is because we want to take advantage of the big numbers. I have in this bundle, I will have a lot of energy states. Okay, I will deal with this first. And then I will look at another bundle, and then I will look at the distribution by thinking in terms of bundles. Okay, so this is really a trick for you to use big numbers. And it's a convenience rather than necessity. Okay, so if I look at one of the bundles, you see something like this. The idea then is I'm going to, for this bundle, this K bundle, I'm going to say that I have energy epsilon K, which is this, which is a good representation of all the energy level, all the energy states in this bundle. So this bundle can have many tens or 20,000, 30,000, big number of energy states. And I'm going to call all of them epsilon K. Okay, so and I'm going to call all these numbers G sub K. So I have one energy value, but I have GK of them times GK of them. Okay, that gives me the advantage of dealing with big numbers. Where are the big numbers? The big numbers is this G sub K, and the big numbers will be N sub K. So I can use Stirling approximation later. Okay, so what are the now this grouping? You see, I did not tell you how to group. I did not tell you explicitly how many levels you have to do it. You have to choose. And indeed, we can go through some number crunching like what we did last time about the number of states, number of particles. But this is really a very similar idea. You can look up the textbook. Okay, the recommended textbook indeed has some calculations there. Okay, but our criteria is the following. We want NK to be large. To be large, how large? Large enough such that you can use Stirling approximation. Okay, and then we want G sub K to be large for the same reason, but not too large. So such that not too large. And because, okay, not too large, because we want epsilon k to be a good representation of the energy states for the entire bundle. For the entire bundle. Okay, so these are the criteria. It's almost like a thought experiment. We are, in our mind, we are asking for big numbers to make approximation. And how can we justify this? You need to put in some numbers, and these numbers will be in the book. Okay, so you will see that this is not a bad approximation, even if you have a large GK, right? Because of the fact that you have very little particles here. Okay, so this and the fact that these are very closely spaced energy levels. So even if you have a lot of them, the distribution, the true distribution in energy is not that much compared with some energy scale. Let's say KBT at room temperature. Okay. Okay, the next question is how to distribute, how to put these NK particles in GK states. I will use levels. Okay, you have NK particles and you have GK levels. How do you do this? How do you make arrangement? And this is just like the coin problem, the head and tail problem. Why? Now, if you have three energy levels, pictorially, how do you draw three boxes? You can draw three boxes like this: one box, two box, three box. These are my energy levels. Okay, I have NK particles. I don't know how many. I need to distribute among them. Okay, now to uniquely define three boxes, I need two partitions. So I can equally just draw two lines. Okay, so if I have two particles here, no particle here, one particle here, so I will have two particles here, no particle here, one particle here. So with two partitions, I will be able to uniquely define three boxes. This is if I turn this by 90 degrees, there will be this kind of picture, right? I will have my energy, and now I take them to be degenerate GK of them. Okay, so I have GK boxes to deal with. I will need GK minus one partition. And I will have NK particles. Okay, how many ways can we have this kind of arrangement? This is basically something I draw here. The equivalent question would be how many ways can I arrange, let's say, three dots and two lines. This is the same. I can put this line here, right? Then I will have 1, 1, 1. I will have, which is one of the possibilities. Okay, so I have GK minus 1 partitions. I have NK particles. If I want to, this question is equivalent to asking how do I arrange GK minus 1 lines and NK circles along a straight line, just like this. So I have some pictures here. Sorry. So let me pull out that picture for you. This one. Okay, so this is some of the possibilities, just like this. Okay, so this is really a binary problem. You either have a circle or a line. You either have a head or you have a tail. So you know how to calculate this. So the number of arrangement. So the answer for this question is I'm going to have this omega, which is the number of arrangements. I'm going to label by K to remind you that this is the number of arrangement to do this operation in this kth bundle. Okay, so that will be the total number of particles, just like before. We have the total number of coin n, and then we already know the answer, right? For the coin problem, if we have what's the symbol? If I have this many head and I will have this many tail, this is the total number of arrangement. So this is just a reminder. Did I use n? Did I use n before? But now this is the total number of coin divided by total number of head. Then there's the arrangement that you have to divide, because these heads are the same, and also the tail, right? So this is the coin problem. Okay, let's just copy and paste. Total number of items will be nk plus gk minus 1, right? You take the sum of this and you take the factorial. Okay, although we cannot differentiate between particles, we cannot differentiate between the partitions, but we can differentiate the partitions from the particles. So we have to do this operation here. So I will have to divide by nk, right? And then I have to divide by gk minus 1. Okay, that's it. That's the answer. So this is the coin problem. Coin problem, just as a reminder. Okay. And now we have more than one bundle. We have many of them. So if you have many of them, you need to consider all possibility, and that will be the product. Okay, this is something for you to think about. Why is it a product, not a sum? Maybe for some of you it's obvious, but it's a good thinking process that you must go through by yourself to convince yourself that this is a product. Okay, so this K runs from basically this index K labels the bundle. If I have 100 bundles, I will take the product from K equals 1 to K equals 99 or 100. Okay. Okay, at this moment, I did not say much about the relative size of NK and GK. I just introduced the bundle. I did this thing. I can even have more particles than the box. I can have 5, 6, 7, but only 3 boxes. Right? There's no restriction on NK and GK. But now I want to begin to make approximation. So be careful. So from here, so the approximation, what approximation? The approximation for the dilute gas. For the dilute gas means I have more particles than the, I have more states than the number of particles. So I will do something like this for you. Begins here. Okay, so hopefully this is clear enough. Okay, so what do I want to do with this approximation? This one can go away. This one. Okay, so I will look at this. I will look at this omega k first. Omega k. How do I approximate this? So first, there are a few steps. One, now the obvious one is this. I have very large GK and NK. This is what I demand. Okay, this is not really dilute, but we know they are large. This is the first step. So in this case, I can ignore this one, right? This GK is such a huge number. I don't care about this minus one. Okay, so my omega k will be approximately NK plus GK factorial divided by NK factorial divided by GK factorial. Okay, and let me use different color. Okay, this is the first thing, better contrast. And the second thing, dilute gas. What do I have? And for the dilute gas, we have a lot more states compared with the number of particles. Okay, so if we want this, so we can make further approximation. So let's do it here. This is in orange color. Okay, further approximation. Okay, first let me write this down. So I'm going to write this. This is still exact. Then the approximation will come next. So let me change to the color. Okay, what is this number? You can just write it out. You have NK plus GK. You have NK plus GK minus 1. And then NK plus GK minus 2. And then you keep doing this until you reach GK plus 1. Okay, and then you have GK factorial. Okay, you can accept this, right? So I just keep reducing by 1 until I reach GK factorial. Okay, how many of them? How many terms here? Okay, they are all together NK terms. Okay, so here, this is so from here to here, I have NK of them. Okay, I keep doing this until I reach here. Okay, so the first thing I can do is I can already cancel this. Okay, now the approximation comes in with the orange color. Now, if GK is much greater than NK, if this is much greater than this, then GK is much greater than NK minus 1. Okay, if GK is so large that is much greater than NK already, if I take 1 away from NK, GK will still be much greater than NK minus 1. And likewise, GK will be much greater than NK minus 2. Okay, so that's where the approximation come in. So GK is much greater than NK, so I have GK only for the first term, first bracket. And by the same argument, because GK is much greater than NK, it will be much greater than NK minus 1, so I will have GK. and then I keep going. How many of them do I have? I will have NK of them. Okay, so the end result is I will have this NK times NK times NK, NK times. So I will have GK raised to the power of NK divided by NK factorial. Okay, so let me warn you here. Or I already say here, but in case you are not very observant. So here, this result is for dilute gas only. Okay, so this is 1. And 2, actually, I don't need a separate category. 2, once you know how to do this approximation, you just really you just copy down this result. So you have the product of G K raised to the power of NK divided by NK factorial. Okay, and this is fun stuff. We are going to come back again when we discuss fermion and bosons. We are going to come back to this step and then see what we can do if we want to treat such a scenario. Okay, so don't forget this. Okay, we are going to repeat this kind of exercise with different way of looking at the problem. Okay, so just a preview. If you look at this, if I have energy levels, just think of it as energy levels, but I rotate by 90 degrees. If you look at the fermion, you will see this is not allowed. Okay, so I will define my fermion such that I do not want double occupancy. Okay, and how do you do the counting? And for boson, this is allowed. I can put as many particles as I like in the same state. Okay, and here we basically do not need to worry about this kind of distinction. And I will ask you again why this is the case once we handle bosons and fermion. Okay, so the M, sorry, let me come back here. The M later, actually the M of this course is to give you the distribution function for this dilute gas, which you might already guess what kind of form you get. And then we want the distribution function for boson and the distribution function for fermion. So that would be the Fermi-Dirac distribution function and Bose-Einstein distribution. So these are coming up very quickly. And the way to get those will be repeating this kind of exercise again and again. Okay, next, let's continue. We want to get the distribution function. So we want to get the equilibrium distribution for the dilute gas. How do we do that? This is something you have done before. Okay, so we want to maximize log of omega. This is the same omega before. Now we want to maximize this rather nasty looking species subject to constraint. Subject to two constraints. So one constraint is we do not want the number of gas particle to change, the number of gas particle in the system to change. And we do not want the total internal energy to change. So these are the two constraints. Okay. So then let's work out log of omega. Log of omega, you take the expression omega, the expression of omega. In the previous page, you have this gk raised to the power of nk divided by nk factorial. Okay, so now you take the log, you have the summation. So that will give you the summation of nk log of gk. Okay, minus the one at the bottom. You take the log. So this is log of nk factorial. Okay. Okay, let me tidy a little bit for you. So we will have summation log of gk, and we have a log nk. Nk is large. This is my demand. I still want a large number of particles, so I will have nk log nk. This is Stirling plus nk. Right? There's a minus sign here. And I would like to group these two terms together. So I will have log of gk divided by nk. Right, I group these two terms together, and then I have another term which is sum over k of nk. And this is just a total number of particles. Right? This comes from here. Just in case. Let me write a bit more. Okay, how do I do n? N is the same as before. Okay, it's just now I don't go to individual energy state. I go to the bundles. I go to kth bundle and ask how many particles do I have here? Tell me. Okay, and then I do the statistic. And the internal energy is similar. I ask what is the energy of the kth bundle, and I ask how many particles you have there, and I do the statistic, I do the accounting. Okay, and next you take d log of omega. So you have this sum over k. Nk, if you differentiate nk, you get 1. So this is, you do the differential with respect to the change of nk. Okay, so then if you take differential with respect to nk, you get 1. You use a product rule, so you keep this. Okay, so there's a dnk. Plus, if you keep nk and you differentiate log, you get 1 over the argument, so you have nk divided by gk. Okay, and then you still have to differentiate everything inside, so you have gk. And 1 over nk to deal with. 1 over nk will give you minus 1 over nk squared. And you have dnk. Okay, and this one we don't care. This is a constant. So plus 0. All right, so now you have this nk squared, so this is gone. And you have gk gone. And then you have sum over k dnk, which is dn. dn is 0. So this term is actually 0. Okay, so finally you have this result. So d log d log is sum over k log gk nk dnk. Okay, so I want to box a few equations. I will need them later. So I will need, okay, I box in strange color so you remember. Yellow, I will box in yellow. This equation I need. So this is log of omega. So this equation in yellow we will need soon. Okay, so this is okay. I will remind you again when we come to this point. Okay, let's start the optimization. Okay, what is the distribution? Equilibrium distribution with respect to the constraint. So as usual, we need to set this to 0 and we need to set the two constraints to 0. So that gives us d log omega plus dn times the Lagrange multiplier, and the Lagrange multiplier for number is alpha, plus the Lagrange multiplier associated with energy, and that is beta, and that has to be 0. Okay, so this is sum of k dk dnk, and for you see this is again my choice of the sign convention. It's a choice. Okay, so I have a minus sign that goes with log of omega, so I will have this g k n k. Okay, plus what is dn? dn is sum over dnk. Okay, so this is alpha, and beta. So du is summing over epsilon k and k. So I will have epsilon k. Sorry, u is sum over u is sum over this product. So du will be sum over epsilon k dnk. Sum over, okay, and I want them to be arranged this way. Okay, and then following the logic before, you know, I can write this. Okay, and I reach my final result. The final result is nk over gk is e to the minus alpha and e to the minus beta epsilon k. All right, or commonly we like to write it like this. Let me save one more line to move gk over there. Okay, so this is our distribution function, and you can see this is again Boltzmann. Okay, so again this is Boltzmann once again. Okay, so remember this K really labels the bundle. Okay, so in this case, this is still discrete. You have K equals 1 bundle, K equals 2 bundle. If you Now, the meaning of this K really is it labels a lot, it labels the bundle. So it has a lot of energy states grouped together. Okay, but if you think in terms of degeneracy, this form really is identical to the form we got before. And if you want to work with a lot of particles, a lot of states, and you don't want to deal with this discrete energy level, you want something more continuous, then you can write a continuous function like this. Okay, so I can just call this e exponential minus alpha, same usual notation, a, which is related to the normalization. And in this case, your G, this degeneracy, becomes the density of states. Okay, and then you have this exponential. Now I don't want, I drop the K. Now this is continuous. Okay, and if we plug in this G of E, the density of states, from the opening slide of today's lecture, I will get the expression, which is a bit complicated. And from there, I can do a lot of stuff. I can do a lot of calculations. Okay, because I can do integration. This is a lot easier than this kind of discrete levels. And if you know the density of states, you plug it in. This is you can do everything analytically. And in this case, just a quick remark: you can get A, can be obtained by integration, by doing this integral. Right? If I count from 0 to infinity, if I count all possibility, you know this product has to give you a number. And what is this number? This is the total number of particle n. So this is again something you can appreciate, because this is like normalizing it, and you can get the A. You can get this constant A to make this true. Okay, so now so far you might really think that we just relabel things and then and copy everything from distinguishable particle. Well, you are right to think that, but of course there will be some differences coming up soon. Okay, so that is the next part. Okay, what do I want to do? I want to look at the partition function. So in particular, I want to calculate. I want to do some calculation to show you what we have done is correct. Okay, so I need more tools, and the tools I want is the partition function. Again, I want to differentiate between single particle or the system partition function. Let's start from single particle, and we can just really define it like this. Although we have now the gas particles are not distinguishable, but I can still discuss. I can still single out one of them and then ask myself, if I take all the allowed energy levels for this one single particle state, what are the possibilities? Okay, so this is still possible. Okay, and it's the same idea. I will just write it like this. I'm going to just sum over the possibility given, right? What are the possibility? The possibility is I can take any one of the bundle, right? So like K equals one bundle, and then how many, what is the degeneracy of that? Okay, so that will be one term. I can go to other K equals 5, the fifth bundle, repeat, and then repeat for all K. This will be my partition function. Now, at this point, this is really the same, mathematically the same as distinguishable particle, but the meaning is very different. And I also want to, now this is the discrete way to write it. And if I take this energy spectrum to be continuous, the continuum way of writing this will be like that. I will sum over all energy, right? This becomes continuous. And then I will have this exponential going in like that. Okay, so I will just sum over all possibility. I will do this later. This is a good exercise, a necessary exercise. I will indeed do this in green color later. But now I want to repeat what we have done quickly with basically with the same steps as before. So I want to calculate my U, energy U. I want to calculate entropy. Actually, we can calculate everything just like before. Once you know the partition function, you have the full knowledge about the system. But here, I just want to highlight the differences for you. So I will calculate U and entropy S. But in principle, we can just repeat the same procedure as discussed in chapter 8, chapter 9, and get all the thermodynamic states. Okay, so let's quickly do the energy and then take a quick break and come back to do the entropy. Okay, U, what's the definition of U? U is sum over epsilon K and K. Right? K labels the bundle here. As I say, since this is mathematically identical to before, you can just plug in the definition of Nk, which we just calculate, and this is A times Gk times exponential. Okay, now this is the same form as before, and we like to write it in terms of log. Now, how do you do that? You remember how we discovered this. We take this function, we take the derivative with respect to temperature, right? Partial derivative with respect to temperature. And then you will recover the relationship, you will discover the relationship between the log of single particle partition function and U. Okay, so this is identical exercise as distinguishable particle. This is something I did before in the class, so I don't need to do it again. The end result is you get N KBT okay. So this is same as before, really. This is the same as before. Same as before. Okay, another one we want to do is to calculate N. N is the sum over K. This is the definition of total number of particle, sorry, Nk. And this is just A times sum over K, Gk exponential minus epsilon K, KBT. So I just copied the definition of Nk, but this parameter A is not relevant when it comes to summation, so I can pull it out. Once I pull it out, I discover that this is just the partition function. So I have A times the partition function. Again, this is the same as before. This is the same as before. This is the same as before. Okay, and what is different will be when we calculate S. Okay, S will be KB log Z. Okay, so I'm going to calculate this after the break. Let's take a 5 minutes break and then come back to look at this. Okay, let's continue. Okay, the next thing is to calculate the entropy. So this is the definition of entropy. Okay, what is this log? This is something I boxed before in yellow. Yeah. Okay, so I need to look at this. Okay, so let's carefully copy this over. So you see I have the sum over k, nk log, and then this big N here. Okay, so I will have this sum over k, nk log gk divided by nk plus big N. So to help you, so this is C yellow box a few slides ago, a few slides earlier. Okay. Okay, what is this? What can we do here? I will. I think I will do it. Just in the. It's one of the assignment questions, but it's okay. Let's just do it completely. So this is sum over k. I have nk here. This is not. I still want you to do it by yourself. Okay, I'm going to do it fully here. But what is this log of gk divided by nk? This is this expression. Okay, where did you get this? I think it's not easy if you have never seen this before. You don't know what to do. Right? So the steps, I will tell you my M. Okay, my M is to give an expression that will be the same form as before, right? I want to, my goal is to link it to the partition function. So you can keep this in mind and then you eliminate things you don't want. Okay, and I will first write down this expression. I don't want this log, it's annoying. So this is really coming from the expression of nk, right? What is nk? Nk is a times gk times exponential. So now I have nk divided by gk will be a times the exponential. Okay, but this is gk divided by nk, so I will have a minus sign here and here, right? You see this minus sign has become plus. Okay, so let me make a note. So this is this is from the expression of nk. Okay, the manipulation of this. Okay, and next, I don't want log. I don't want log of A. So I want to eliminate that. Okay, this is again very, very nice exercise. Now, if I do this sum over nk times minus log A, let me first write this minus log of A. If I have this sum over nk times this give me a big N, right? Because I sum over k times nk, right? This is the total number of particles, so I will get this when I multiply by this product. Okay, but here you need to be careful because for the second term, you cannot do this. The second term, you have sum over nk epsilon k because there's an index k here. So this summation sign sees both the epsilon and the nk. So you should work on the product and that will give you u instead. Okay, so this is done. This all of these are the parameter I want. Okay. Okay, now I can eliminate. I can eliminate log a using this line here. So I will use star from this slide. So use star from this slide. I can eliminate log a. Then I will get my n, log n and log z. Okay, so this will be kb minus n remains, and log a using star, I will have log n minus log z plus u kbt plus n. Okay, kb, I have n log, you see I already get the form I like. I have single particle partition function. I have this n multiplying it. It's promising. And here I have minus n log n plus n. So I put it in the form you like. So this is n log n minus n log n minus n. This is plus n plus u kbt. Okay, so plug in the formula. Sorry, expand this. I have n kb and log. Okay, plus the definition of u. This u from up there, I have the expression of u, which is this is n kbt partial derivative okay. So this is this term here, and we still have this term to deal with. This is Stirling approximation, n log n minus n, so this is n factorial. So I have minus kb log n factorial. Okay, actually I changed color. Okay, now it's important to pay attention that this is S, this is entropy. And if you compare with what we learned before, the entropy here, right? You see you have this n kb log z, you have this u over kbt, which I gave you the full expression. Right? You have this term, you really have this term, and this term. Okay, so these two terms are there. But here for your gas, you have this extra. This is extra term. Okay? Right? If you compare this with what we learned before. But I told you long ago that if you remember to use the system partition function, the partition function for an assembly, you get the same expression. Okay, so provided that you use this expression for this partition function for n assembly of n particles. Okay, so I told you before, but here this is show up here. Okay, so if I take, so if I take this Zn to be single particle partition function raised to the power n divided by n factorial, I will get the same expression. Now you can do it by inspection, right? Because if I take this log, I will have, so if I take n log of this, I will get n log dsp minus log n factorial, and this n factorial, log n factorial is here, multiplied by kb. This one multiplied by kb is this thing here. Okay, so this is consistent with what I claimed before. And what about the middle term? The middle term is also fine. It's also under control. Why? Because if I do it this way, and I take the derivative with respect to temperature, this term will disappear. I will only end up having this term. So that is why I get this the middle term here. Okay, so if I do it this way, I will be able to, if I write it like this, then I can write as in terms of Z sub n plus kb t okay, so this is the result. Okay, and it's consistent. Okay, so the justification really is this. You need to write it like this, and you can check the energy, right? You can actually, you already know. I already say that if you check the energy, it doesn't really give you a trouble whether you have n factorial or no n factorial because of this derivative in front. You differentiate with respect to temperature, but this does not depend on temperature. Okay, but the problem really show up in entropy, and this entropy will be wrong. I will show you it's really wrong if you do not include this n factorial. You cannot detect it in the internal energy, but you can detect it in entropy. Okay, and let's stop at this point first, and I will show you why this is wrong very soon using a concrete example. Okay, but I want to write a little bit more. Actually, what I want is for you to remember this. Okay, now this n factorial, this is a bit mysterious, but it's not. Now we discovered this by looking at the form of entropy. But at the same time, you can kind of appreciate this. If your particles are not distinguishable, you will have less arrangement, and that's why you will have to divide by something, and this something turns out to be related to the system size, and this is this n factorial factor coming in. Okay, but before I can show you how wrong this will be if you use the wrong system partition function. This is what I mean, the system partition function. This is single particle, this is the system partition function. I keep saying this, so it's better to clarify than system partition function. Okay, if you use the wrong system partition function, something else will show up. Okay, so let's get to that point. 18, 19, 20. Okay, so to do that, I really want to really put in some hard work to deal with this integral form of the partition function. Because we can get some very concrete result if we really spend time to deal with this. Okay, so let's go to that point. So this has to do with this is a concrete application for monatomic gas. Right, we have been talking about gas. Okay, so what can we do to really get some very satisfying results that you will be very happy over the reading week? So this comes back to the opening slide again. What did we do with this particle in the box problem? Okay, so this particle in the box, we are talking about a system with, when we solve the particle in the box, the Hamiltonian contains only the kinetic energy. The kinetic energy and no potential energy. And the kinetic energy has the form of translational kinetic energy, P squared over 2m. So this is translational. Okay, and therefore we are actually already solved the problem for this monatomic gas. Right, so we have a collection of gas particle, and this particle is formed, let's say, argon gas. So one atom is one gas particle. We are not talking about molecule. We are not talking about, for example, oxygen, where you have two oxygen atoms, and these two oxygen atoms form the oxygen molecule, and this oxygen molecule can have rotational mode, and they can also vibrate because of the bonding between them, right? And in this case, if we talk about a simple case like this, we only have a simple kinetic energy term, right? And that is why we actually already fully solved the problem, and we can get very good prediction now. Okay, so what can we get? So this is a good model to describe monatomic gas. Okay, so for example, argon gas or helium gas, if you like, but not oxygen, not carbon dioxide, not nitrogen. Those are diatomic case, and that will be discussed in the next exercise class, about 2 weeks from now. Okay, so the partition function, let's write down the partition function. Let's now we already have the partition function for the dilute case, right? That is how we get the that's how we get the Boltzmann factor. So the integral form will be like this. This is something you saw before. Okay. So let me repeat. This is the integral form of the partition function for the dilute gas. Okay, so this is for the dilute gas. Okay, if we want to discuss the monatomic gas, we need to somehow integrate this knowledge into here. And what can we do? We will have to manipulate this term, right? Because this is coming from the particle in the box problem. Okay, so if I plug in the appropriate density of states in energy, I will be able to discuss a dilute gas, a dilute monatomic gas. Okay, so so if I write this G of E in, so this is 4m pi times volume divided by h cube 2me. This is from before. This, if I plug this in, then I can discuss dilute monatomic gas. Okay, so if I do it that way, if I plug this in, I don't want to rewrite this. I will have this 4m pi b whatever multiplying this exponential factor. Okay, so in the end, you can pull out all the constants. They are not seen by the integral. 2m kbt and 0 to infinity. Okay, so far nothing profound. I just arrange it so that we are ready to manipulate the integral. Okay, and now I will tell you what to do. So we are going to let this to be x squared. And you will realize this is one of the standard integral that you can look up the table or you'll be given the value of the integral. Okay, so you need to, the steps are just routine. Okay, you just let this to be x squared. And then don't forget to deal with this d epsilon. And in the end, you will use a standard integral like this. So this integral give you, try to rewrite this into the standard integral minus x squared dx. And this is pi over 2. Okay. Right, so you have x squared here. You are almost there. And this one, you get 1x here, and then you get another x from this d epsilon. Okay, so you get x squared here, and then you need to manipulate the limit. You need to justify that this is an even function, and when you integrate, what is the integral? Okay, so in the end, you will pull out a few more factors, and the end result is this. I'm going to write it in this form. So you get the volume V, and you will get 2m pi kbt divided by h squared. Okay, so this is the partition function I want. Okay, remember, keep in mind the logic here. Right? How do we get from this line, plug in this line to get here? And this is the ingredient for the sausage machine. I'm going to use it soon. Okay, my aim is to get precisely this form to play with. Okay, but before we use this, I want to say a few things about this factor. And I would like you to answer me a quick question using the chat. Okay, what is the unit of the partition function? Okay, quick. What is the unit of the partition function? And send me a private message. Anyone? What is the unit? What is the dimension of the partition function? You're thinking, or because it's rather slow, I would expect this answer right away. Were you thinking, or you just came back? Okay. Okay, thank you. Now I get 5 answers. Correct. All of them correct. Okay, this is dimensionless. This is dimensionless. And this is volume. Okay, so these, to make this dimensionless, this has to be some inverse volume, right? Okay, what is the meaning of inverse volume? Inverse volume means this is some kind of number per unit volume, right? The thing in the square bracket. Sorry, the thing multiplying V, including this 3/2. Okay, so this has to take the unit of 1 over volume, some number per unit volume. So this is some form of concentration. So this whole thing takes the meaning of concentration. Okay, so this is from dimensional analysis. And it has to be some kind of concentration. And this concentration is called the quantum concentration. So this N, Q is quantum, the Q label is quantum concentration. Okay, I would justify why this is quantum later, but I want to write a bit more. So actually I want this slide before. Okay, I need this slide. Come back to here. Okay, so the point is this. We have been looking at the system which is dilute. We keep saying dilute, dilute, dilute. But this gives you, now if it's dilute and you do it properly, you get, so for dilute system, we know actually we can write it like this. For dilute indistinguishable volume of gas particle, we can write this partition function like this. Right? All this we already mentioned. It's important that you synthesize all this knowledge. Okay. Now this gives you another way to look at dilute. How do you justify dilute? You look at the concentration of your system. Suppose you have this particle in the box, you know the size of the box, you know the number of particles, you have some concentration N. Okay, so this is concentration. This is the this is not the quantum number N, and this is not the occupation number N, this is the concentration. And if this is much lower than this NQ, you are in the dilute limit. And actually, if you really go home and work it out yourself, this is the same treatment as the one I did when I calculate the number of states and the number of particles. You will realize they are the same. You will see a lot of factors there, and you can recast the language of that into the language of quantum concentration. Okay, and if you satisfy this, you are in the classical regime, and hence quantum for otherwise. Okay, and you know why? This all terms can be stringed together. If I have a dilute system, a dilute gas, I can ignore the interaction between them, and I can use classical statistics, and the classical statistic, if you work backward, but all these steps are logically connected, you can get this partition function. Okay, and when we derive this, I implicitly assume this NK much lower than GK. The number of particles is much smaller than the number of states. So that is somewhere used. This is the information used somewhere in the derivation. Okay, so the opposite limit is this. If I have n, which is much greater than n cubed, I will need quantum statistics. So this is coming up soon. This is next chapter. Okay. Now, so how do you calculate it? Again, the same. You calculate the number of particles per unit volume, compare with this number here. And you can see this NQ is related to temperature. Okay, and that is also reassuring if you take a dilute gas. Now, actually, the other term is called ideal gas. If you cool it down, you don't have an ideal gas anymore, right? When you cool it down, this benchmark quantity you use for comparison is going lower and lower and lower, and this make this n, if the number of particles and the volume doesn't change, you will get closer and closer to NQ. Okay, and the other example is you take the number of electrons in metal and calculate this number and compare with the corresponding quantum concentration. You will find that you need quantum statistics. Okay, so this is a good remark to make here. And now, as promised, I want to justify a little bit why we call this quantum concentration. Why quantum? Okay, it's a bit of detour, but not too long. The detour is the following. We need to if I don't want to discuss volume, right? If I don't want to discuss number per unit volume, I can also recast this in a length scale. Okay, so I can, rather than compare the concentration, I can compare some length scale. That's to say, if my particle-particle distance is above certain threshold, I will have, I will be in one of the regime, right? So this length scale can be easily defined because I have volume, right? This is NQ is 1 over volume. So 1 over NQ would have the dimension of 1 over NQ will have the dimension of volume, but I want length, so I have to take the cube root. Okay, so I can define some kind of scale, length scale, like this. I take this and take this power. So this is a length scale. Okay, this is definition. This is definition. I define some kind of thermal length. I use thermal length first. Right? What is this this thing? Okay, so if I do it this way, I will get H. Right? This is H cube. I take 1/3, and I will get 2 pi mkbt. Okay, hopefully this will already give you a hint why this is called quantum concentration. So so the equivalent of the n much lower than the quantum concentration. This condition is equivalent to having the particle-particle distance much larger than some characteristic length scale. So in such a case, I can use classical statistics, the Boltzmann distribution we discovered. Okay, in fact, if you look at this thermal length scale, I could also call it the de Broglie wavelength, because these two are related. De Broglie by a constant of the order of 1. Not exactly 1, but of the order of 1. Of the order of 1. That is why this is called quantum concentration, because the length scale is set by de Broglie wavelength. Okay, and very quickly, how do you find this de Broglie wavelength? De Broglie wavelength. You can be found like this. You first write down the kinetic energy. I told you this is translational kinetic energy, and this is of the order of kBt. I don't want to argue about this constant in front. That is why I don't want to argue too much about this. Okay, let's say there's some thermal energy kBt, that the particles in the gas take advantage and turn it into translational kinetic energy. Okay, then I can write it like this. Okay, and then I basically have it. This p square, I can just use h divided by lambda de Broglie, and that will be around kBt. Okay, and if you rearrange this, there's some constant here which we haven't done it properly, but this is hand waving. Sure, but you immediately get something of this form. Okay, so this is 2m kBt. If I move this to here, then I have lambda squared. Okay, if I use this treatment, this alpha is square root of 1 over pi. As I say, of the order of 1. Okay, so that is why we can call this the quantum statistics. Sorry, the quantum concentration. Okay, this is an aside, but what I want is to do more calculation. Okay, we already justified this. And now let's continue. All right, so first, I want, as a reminder, we are dealing with the monatomic dilute gas. So first, I want to ask, what is the internal energy? The internal energy is kBt squared times this term. I already told you we need to use this form. Okay, and then let's plug it in. We will have log okay, and then I will have kBt square n log single particle partition function minus log of n factorial, but this is not dependent on t, so that drops out. That will disappear and become 0. Okay, now I will write one more for you, but this will become 0. Okay, so in the end I have n kBt squared, n kBt squared okay, this is when I need my partition function. Okay, now but don't worry too much, because the advantage is we are taking log. So once we take the log of all these products, we turn it into sum, right? So we will have log v plus log whatever. All we need to care is the term with t, because this is the only term that will return a non-zero product. Okay, so I can write it like this: n kBt squared. I will have log of t plus a bunch of terms that are not dependent on temperature, terms independent of T. Okay, so this will be 0, and this 3/2 I can pull it out, and can nkbt square, and then I have log T. Log T, differentiate log T, I get 1 over T. So this is the famous result, which you must have seen somewhere. So this is a result which has to be framed. This is so famous. This is the internal energy for a monatomic ideal gas. And then we got it really by doing all these steps carefully and honestly, and we recover this famous result. Okay, why this is famous? So first, this is a standard result from kinetic theory of gases. Kinetic theory of gases. And second, it shows that the internal energy of an ideal gas is only a function of temperature. Another result, another famous result. And third, it allows you to calculate the heat capacity. The heat capacity can be obtained by the temperature, another temperature derivative, and it will give you 3/2 nkb. This can be appreciated very much. Okay, you have that many, your particle can move along all 3 directions, so you have 3 degrees of freedom, and each one will give you a 1/2 kbt, and you have m particle, and that's this total internal energy. If you take the derivative, you get the heat capacity. Okay, so this is a famous result. Okay, now I want to push on a little bit. If you need to go, I will let you go. I have a bit more to cover. Okay, and you have the video as usual. The next thing I want to do is to calculate pressure. Now this is a fun calculation. I want to calculate pressure. Why do I want to do that? And how do I do that? Okay, I will tell you how to do that. Okay, so first I write down the differential form of the Helmholtz function. You see, what you learned in thermodynamics is not wasted. Okay, and now you know how to do the calculation. You take the partial derivative with respect to volume, right? Okay, and how do you do that? There's a minus sign, and f is related to the partition function with a minus sign, so you turn it into a plus. So that's the first thing. And then you differentiate something with respect to volume, keeping temperature constant. Okay, and that something is kBT log Z. Okay, I told you temperature is constant, so you can pull it out. You have kBT, and you have this log of system partition function. And this system partition function, this is I don't want to write this anymore. Okay, you know what I meant. So this is n log Z and then log n factorial. And as usual, this is not depending on volume, so this will be 0 because you are differentiating with respect to volume. And just like the case of the previous exercise, this n can also be pulled out. This n can be pulled out. You look at the partition function, and because you take log, everything will disappear once you take the derivative with respect to volume. Okay, so you look at the partition function. This is log V plus log of this whole thing. This do not depend on volume, so you only have log V to worry about. Okay, so you only have log V to worry about, plus a bunch of terms independent of volume. Okay, I think this ought to be the high point of this chapter. This is NKBT. And you differentiate log V, you get 1 over V. This is the equation of states you must recognize. So this is reassuring. We are dealing with an ideal gas. So this is the ideal gas equation of state. Again, comes from a completely unexpected direction, probably. But if you pay attention, you should suspect that this is the case. This is what we were doing. Okay, the next is entropy. Entropy is what went wrong if you do not use the correct partition function. For internal energy, for Helmholtz function, if you use the wrong one, lucky you can still get the correct answer. But if you try to do entropy, you get the wrong answer. Okay, so I will tell you the correct answer. If you do it properly by using the correct system partition function, you get this result. So I will write it down for you. And then now this is again the same sausage machine. You just plug it in and do it carefully. 2 pi m kb and then h square minus log n plus. Okay, this is if you use the correct function. Okay, the incorrect one, I will write it in red. This is the wrong one. So the S wrong. Wrong means you use the partition function without this n factorial. So you will get n kb. You still get log b. You still get 3/2 log t. You still get this log of 2 pi mkb. And you get a different constant if you use this, which is wrong for this, for gas. Okay, now this is very interesting. How do I know this is wrong? Is there any way to tell this is wrong? Now, there's no mystery here, okay? If you plug in this, and well, the way to generate these two functions is the following. You take the definition of S, and you do all this standard treatment, you get this result. Okay, so now you plug in different form of Z. Okay, one is and the partition function is this one here, this guy. One you raise to the power of n, plug it into the expression for S. One you raise to the power of n and divided by n factorial, and plug it into the expression for S. You get these two expressions. So try, please try. And why is this wrong? Now the reason is this. I think you have seen something like this in midterm. So if you do it correctly, then the correct expression must respect the fact that entropy is an extensive quantity. So the correct expression will give as an extensive quantity. You have to, this is something we know. This is something we know. It has to be true. Okay, and how do you do that? Now, so we simply double the system size and see whether the entropy double. Okay, so if you take V goes to 2V, if you double the system size, volume increased by a factor of 2, and the number of particles also increased by a factor of 2. You take the same system, put it next to each other, and then just treat it as a new system. And the entropy has to scale accordingly. We learned many times in this course. And look at this. If this n is V goes to 2V, n goes to 2n, then you have this log 2 here and this log 2 here, they will cancel. So everything in the square bracket is well controlled. Okay, and you get the doubling of the entropy by this n here. This n becomes 2n. So the new S becomes the twice of the original S. Okay, and the rest are intensive. This T doesn't change, or this constant doesn't change. But this nice property does not appear here, because now you scale the system size, you have 2n here, and this one you have this log 2, which you don't have any way to get rid of. You have this 2v here, right? So you have you do not scale the entropy properly. Okay, so that is the way to tell that you have to use the correct partition function to get the correct expression for entropy. And this correct expression for entropy, this expression is very famous. Sorry. This expression is called Sacku-Tetrode equation. And it went into one of the final exam questions a few years ago. Okay, so that's all for this lecture. We covered quite a lot today, but because we have this reading week, you won't see me again for the next 2 weeks, and I hope you can have more materials to digest. Okay, so thank you very much. Enjoy your reading week, and don't forget the exercise classes. They are important materials that I won't have time to cover, but I need them for the last 4 lectures. Okay, thank you very much.
Professor, I have a question.
Okay, I'm waiting for you.
In page 22 of the note.
Wait a minute, can you speak up?